So this is basically saying that in general, in quantum mechanics, we can associate with an observable an operator. So, this thing is not an operator, it's just a number, but in general, this is a differential operator, a linear differential operator. And this was later generalized to show that it's actually going to be a Hermitian linear operator, okay? And similarly, we can show that the energy of the particle is an operator which is given by minus h squared by 2m del squared by del x squared plus v of x. Okay? So I think there are other operators one can consider, not just, for example, and we might get to that. One is angular momentum, and then there could be, say, spin. So these, and we will see that in general, these are all operators, okay? So sorry about the mix-up, but I think it's very instructive to make mistakes in class, because that's how people learn, and you should always know that we all make mistakes. So let me just finish with a chart, and the chart is going to be, physical quantity so physical quantity here, and in the position representation, which is where the wave function is given by psi, and the momentum representation, where the wave function is given by A. So, okay, so wave function in position space is psi, just repeating what I said, and in momentum space it's A. Probability density in position space is psi bar squared. In momentum space, it's a squared, modulus of a squared. And position observable, in position basis, it's x. It's but in momentum, it's actually, and the momentum observable is, we just saw, h by I, d by dx. However, in the momentum representation, the momentum observable is just p, and the position observable is ih bar d by dp. Okay. So we have seen this, and this. You guys can figure. So basically, what you can do is that you can take the Fourier transform of these relationships and show this. And what I'll do is that in the next class, I will introduce a necessary machinery, essentially the Dirac delta function, so that you can do the Fourier transform. Okay. So any questions? I'm sure there are lots, but any questions that we can discuss?
The position observable in momentum, if I apply that in a wave function, I get the position.
Exactly. Yeah. So the position observable is just is an operator, but it just acts by multiplication. X is just a number, right? X is just it's not a differential operator. So.
I have a question.
Sir, I have a question.
Oh,
okay.
You first.
Saif, go first.
Saif, you said first, so yeah.
Okay. So basically the mistake that we made was instead of having two functions of x, instead of having three functions of x, we had two functions of x in our product.
Yeah.
Okay.
Yeah, basically I forgot the x. There was a factor of x, and when you did the total derivative, there would be an extra term of x, and that's the term that will survive.
I see. Okay.
Okay.
So product rule of three terms.
Yeah, exactly. Yeah. Okay, yeah, Nyan?
Oh, sir, যে আমরা phase space এ
Oh, sorry. Before you say that, thank you, Sai, for being. Let me just say thank you, Sai, for saying that the position we made, the mistake we made, the mistake was made by me, but not we. But anyway, yeah, sorry. Yes. You were saying, Nyan?
Sir, মানে phase space এ মানে এটা তো পজিশন এর ইয়ে থাকে আবার মোমেন্টামের ইয়ে থাকে কোঅর্ডিনেট থাকে তো এখানে আমরা যে বলছি পজিশন স্পেস মোমেন্টাম স্পেস এটা কি মানে এভাবে ইয়ে করা যায় যে আমরা ফেজ স্পেসে জাস্ট পজিশনের কোঅর্ডিনেট গুলোতে কোনো একটা পার্টিকুলার মুভমেন্টকে ইয়ে করতেছে আর ফেজ স্পেসে জাস্ট মোমেন্টামের অ্যাক্সিস গুলোকে মানে ওই এরকম ভাবে কি ইয়ে করা মানে ইমাজিন করা মানে ইন্টারপ্রেট করা যায়
Nyan, a second, let me turn off the alarm, and then I'll answer your question. Okay, so that's a very interesting question. And so let me just repeat the question for everyone. What Nyan is asking is that when we are talking about, position space and momentum space, and we're talking about probability distribution, are we talking about, say, phase space? As you know, phase space consists of, in classical mechanics, a point in phase space tells you what both the position and the momentum of the particle is. And so what Nyan is asking is there some sort of probability distribution on phase space, and whether we are just kind of integrating out, say, the probability distribution of the momentum and talking about the probability distribution of the particle position and vice versa. Is that correct, Nyan?
Yes, sir.
So that's actually a very good question, because the answer is actually no. It turns out that even though you can define probability density on position space and momentum space, you cannot define in quantum mechanics a probability density on phase space. It turns out that it is not possible to have a distribution, a positive definite distribution on phase space in quantum mechanics that is consistent with the mathematical structure of quantum mechanics. Okay, there are some functions. So it turns out that there are some functions which you can define, which might have the same kind of properties of the probability distribution in classical mechanics, but they are not positive definite. They may become negative. And such functions were first considered by Eugene Wigner, and they're not unique. And of course, probability functions are never unique on a phase space. And these are called Wegner functions. Okay. So Wigner functions are distributions on phase space, but they are not they are not positive definite. But they do, that in classical mechanics, probability distribution, probability is conserved, of course, and therefore, and that fact is expressed by Liouville, the Liouville theorem. And what Liouville theorem tells us is that if we take the phase space of a classical system, and if you consider a small blob, so then that volume, it spreads out, of course, and it becomes something very complicated over phase space, but the volume of that blob remains invariant, and that's that's a expression. That's a expression of conservation of probability in a classical sense. And it turns out that, because the Wigner functions, it does satisfy such properties, but you cannot give it a strictly probabilistic interpretation. So yeah, that's a very interesting question, and the answer is no. But Wigner functions do have some sort of pseudo probability interpretation.
So
And
do they have interpretations in quantum field theory? Quantum mechanics যেহেতু নাই আর?
no, I mean, quantum field theory doesn't really improve on these things. What quantum field theory does is that it allows you to treat systems where the total number of particles is not conserved. That, consistent with charge distribution, you can change the number of particles. But this situation of the space is not improved in quantum field theory. Okay.
All right, sir.
Any more questions?
I have one more question. So energy has the operator for momentum and position inside of it, right?
Right.
So is it that, I mean, I might be misinterpreting this, that's why I'm asking. Is it that energy is always uncertain, because if you decrease the uncertainty of one, you increase the uncertainty of the other?
No. It means that you can measure the energy arbitrarily with arbitrary accuracy, but that means you're giving up. If it's a free particle, you can measure its momentum accurately as well. But if it's not a free particle and there is a potential energy, then you're saying that you can't measure both the energy and the position of the particle, or the energy and the momentum of the particle accurately.
I see.
With arbitrary accuracy. So you'll see that because the momentum operator is a differential operator, so it's h by I del x. That means that if you apply it on, and if you have x and if you apply it on some wave function, it is not zero. The commutator is not zero. Instead, it's I h bar psi. In other words, the more generally, there's a minus sign. More generally, the momentum and the position operator, they satisfy this so-called Heisenberg algebra. Okay.